One small step for man, one giant leap for mankind.
Like the dawn, a new era of flight is on the horizon. A time that will change our relationship with the sky. Air travel is no longer runway to runway, but point to point. Following in the path of the helicopter and airplane comes Tiltrotor, an aircraft that will change the face of aviation. I'm Craig Schmidtman. Join me and Tiltrotor experts as we look at this remarkable aircraft and how it will carry us into the future. Vietnam, the helicopter war. That was the image for most of us, and there was a great measure of truth in that picture. Vietnam redefined the chopper's military missions. It was a testing ground for our first large-scale tactical helicopter operations. Gunships brought a new dimension to battlefield air support. Helicopter troop transports, such as the CH-46 Skyknight, provided a tactical mobility previously unknown. Helicopters took center stage in Vietnam, but it wasn't the first time they saw combat. Korea, the police action fresh on the heels of 6 years of bloody global conflict. Offering more of the same to civilian and soldier. But there was something different in the air. Korea was the first true helicopter war. Helicopters carried troops, performed search and rescue, but it was their use as a battlefield ambulance that brought them the most acclaim. Harsh terrain and unforgiving elements have always plagued men at war, and Korea was no exception. Police action or not, the toll was high. But wounded soldiers in Korea had an advantage their counterparts in previous conflicts didn't. When the call for help went out, evacuation by air meant care was minutes instead of hours away. The Korean experience tested this new technology and encouraged further helicopter research and development. It also opened the door to new schools of thought regarding vertical flight. Some experts believe the helicopter was an intermediate configuration. To them, the future belonged to something called convertiplane.
Well, it was right after World War II. The research and development was really in high gear for all types of aircraft. And the helicopters had just come on the scene at the end of World War II and made their little niche. and they were starting to get FAA certification and becoming commercial machines and so forth. And it was at the first convertiplane Congress in Philadelphia in '49 that one of the conclusions was that the maximum speed of a helicopter will be about 160 knots. So industry and government should start some type of convertiplane effort to marry the low-speed characteristics of the helicopter with the high cruise efficiency of the airplane. And there was a wide variety of vehicles that came out of this. And here we had the tilt wings, you had fan and wing, you had the tail sitters, the Pogo tail sitters, and the Ryan X-13 was a jet lift tail sitter. All these things were tried. But about this time, a small group of engineers formed Transcendental Aircraft and built the first tilt rotor. It was called Transcendental G1, I believe, something like this. And it did fly as a helicopter, and it did convert. It never, I don't believe, made a full conversion. They got to about 70-degree power angle, but they had gotten to the point where 95% of the weight was carried on the wing. So you can say they demonstrated the ability to go from rotor lift to wing lift.
One of Transcendental's key engineers was Robert Lichten. Although heavily involved in the design of their first tilt rotor, Lichten left the company and joined Bell Helicopter before the 1G ever flew. Bell Helicopter's Ron Reber.
So he received internal funding initially to do some research, to do some analysis and some primary research. He then went to the Army and Air Force, and the U.S. Army was buying aircraft. They were buying airplanes and helicopters, but the Air Force was kind of their purchasing agent, kind of like the Navy and Marine Corps now. The Navy does the purchasing. So Lichten convinced not NASA, but the Army to fund the program and to prototype 2 aircraft.
Known as the XV-3, Bell's first tilt-rotor design was proposed in response to the U.S. Army's 1950 convertiplane competition. As one of 19 designs submitted, the XV-3 survived through the design study, wind tunnel, and mock-up construction phases to be chosen as one of 2 to go on to prototype construction. The other concept to fly was a compound helicopter, the McDonnell XV-1, but it never went beyond the prototype stage. The rollout of the first XV-3 was on the 10th of February 1955 at Bell's facilities in Fort Worth, Texas. After extensive ground tests, it conducted its first hovering flights on August 11, 1955, with Bell's test pilot Floyd Carlson at the stick. The early flight test program went smoothly as the envelope of the XV-3 was gradually expanded. But 2 months into the program,
we had an accident early in the program. We had a wing pylon instability.
This is where you'll get a rotor exciting the wing, or the wing exciting the rotor, and the structure starts to go. All the structure in an aircraft has a natural frequency, and you don't want to excite that frequency with a rotor beat or something of this nature.
Now, if you recall, the aircraft had 3-bladed rotor system and a very long mast on the ends of the wings, very soft wings, 1 reciprocating engine in the fuselage. All of the control system actuators, all the hydraulic actuators, were actually mounted in the fuselage. So you had a very soft control system. You had a very long mast with a rotor system mounted on top of it, and its natural frequency just happened to coincide very closely with the natural frequency of the wing. And as a result, when we got into full forward flight, the 2 modes started driving one another. It went unstable, essentially. And when you start getting into this instability point, the aircraft would become uncontrollable. And this actually happened in flight, and we had a crash of the first aircraft. The pilot was not killed, but he was severely injured. So we went back to the drawing board at that point and looked at what we could do to get away from the natural frequency problem, and that's when we went from a 3-bladed rotor to a 2-bladed rotor. And we also stiffened up the wing structure. The wings were soft torsionally and bending-wise. So we stiffened those up with struts. So later pictures of the XV-3, you see struts on it and different rotor system. We then contacted NASA, and NASA Ames had just opened up their 40 by 80 wind tunnel, and we did some testing of the aircraft full scale in the NASA tunnel to determine whether or not we had solved the instability problem. So that's really where NASA came into it.
The second XV-3 accomplished the next major milestone in the program, a full conversion from helicopter to airplane mode and back. This took place on December 17, 1958, with pilot Bill Quinlan at the controls. In fact, this was the first complete conversion of any tiltrotor in history. The XV-3, although the first successful tiltrotor, wasn't the first designed. In the late 1930s and early 40s, England and Germany produced tiltrotor concepts on paper. In the U.S., one visionary designed a 53,000-pound model in 1946. None of these designs were built, but they were the first steps in the direction the tiltrotor would ultimately take. By 1958, of course, the XV-3 had the first tiltrotor conversion to its credit. It went on serving as a testbed until the program ended in 1966. During this time, it continued flight tests in both Fort Worth and at Edwards Air Force Base, California. From Edwards, the XV-3 went to the NASA Ames Research Center at Moffett Field Naval Air Station near San Jose. There it was used as a full-scale wind tunnel model to study the dynamics of wing and rotor interaction. Here, unfortunately, it met an untimely end.
We did follow-on studies, analytical studies on what the instabilities were caused, what caused the instabilities and how we could overcome them. We did some more wind tunnel testing, and ultimately, between NASA and Bell, we funded another wind tunnel entry into the tunnel at Ames with the full-scale XV-3, and that's when the aircraft came apart in the tunnel. We were testing. In the final phases of testing, we had proven pretty much the flight conditions, and we had proven that we had solved the wing rotor instability problem, but we had a mount failure in the tunnel. So the aircraft didn't fail, the mounting structure did, and as a result it blew down the tunnel.
In addition to its aeroelastic stability problems, the XV-3 was deficient in other areas too. For example, its performance was extremely limited. Unless the XV-3 carried minimum fuel and the outside air temperature was cool, the 450 horsepower Pratt & Whitney R985 radial engine could barely manage powering it through a vertical takeoff. Stall or short rolling takeoffs were far more common during the XV-3 program. The power-to-weight ratio of the R985 was not ideal for the tiltrotor concept. This problem was compounded by the fact that the aircraft was constructed with materials typical of the period. But the deficiencies of the two aircraft built and flown were not unique to tiltrotors. Instead, these were problems that the helicopter and aerospace industries in general were struggling to overcome. Despite its limitations, the XV-3, when compared to the pure helicopters of the late 50s and early 60s, more than doubled their 70 to 80 mile-an-hour top speeds. During the course of its 250 test flights, 110 conversions from helicopter to airplane and back, as well as 125 hours of flight time, the XV-3 proved the validity of the tiltrotor convertiplane concept. This was 1966. Ron Reber.
I think the XV-3 proved the concept of taking off vertically and then transitioning into airplane mode. We proved what Lichten had believed 10 years earlier, that it could be done and it was a viable concept. So the XV-3 showed that it could be done, and in fact it was a relatively stable aircraft. It was way ahead of its time, as it turned out. The difficulties that we had were not so much in the concept, but in the way that the aircraft was put together because of the technology that was available at the time.
By the late 1960s, two companies, Bell and another player, Boeing Vertol, were pursuing solutions to the tiltrotor puzzle on their own with additional funding from NASA, the Army, and the Air Force. Vertol, well known for their tandem rotor helicopter designs and originally founded by helicopter pioneer Frank Piasecki, switched their design emphasis from tilt wings and began a series of tiltrotor model tests, including 3,500 hours of wind tunnel time. As the 60s ended, Bell independently built a 9,000-pound full-scale tiltrotor mock-up. This was their Model 300. This work in part led NASA and the Army to decide the XV-3's problems had been solved. Together, they funded another tiltrotor proof-of-concept flight test program in 1972.
Then we went into a phase that NASA and the Army wanted to look at a follow-on program, an actual flight program. And we came up with the Model 300 and later the 301, which is the XV-15. We did some analytical studies and some more design concepts and looking at powertrains. And in '72, NASA had a proposal effort, request for proposals from the industry to actually build some more flying prototypes, proof of concept. We, Bell and Boeing Vertol, actually competed one against the other, and we were both in the middle of doing wind tunnel studies and our own analysis. Bell won out over Vertol and got the contract to build 2 flying prototypes. So that was the beginning of the XV-15.
Shorty Schreers describes the XV-15 and the tiltrotor concept.
Well, the tiltrotor is a novel type of aircraft that incorporates the low-speed capabilities of the helicopter, plus it can convert and fly as an airplane. Some people say you can't have the best of both worlds, but you can. Now, the XV-15 tiltrotor research aircraft has 2 rotors, one on each wingtip, which when in the vertical position can operate as a helicopter. And then on pilot command, the conversion can be placed, these pylons can be placed at any angle, so they are in effect speed control. The man can select the pylon angle and the fuselage angle that he wants and fly at that speed. So it gives the pilot a great deal of flexibility. And then it can go all the way to airplane mode, and then it's a twin-engine turboprop airplane. Now, it also is capable of going directly from helicopter to airplane mode. And it will do that in about 13 seconds. So you're accelerating from hover to 160 knots in 13 seconds. Pretty good kick. And the power plants for these 2 rotors, there's one on each wingtip, and they're basically the Huey Lycoming gas turbine engines. They've been modified slightly to run in the vertical position as well as in the horizontal position. And to protect the aircraft from an engine failure, they're cross-shafted together. So if you lose one engine, you keep both rotors turning. All the pilot sees is a loss in power, which he compensates for by pulling more power. The conversion process is done through screw jack actuators on the pylon, and they are also cross-shafted together, so that if you lose a hydraulic system, you can still convert. Each conversion actuator has its own hydraulic system, has its own electrical system. So you can suffer an electrical failure and a hydraulic failure and still convert. People always ask, what happens if you can't get them up? Well, my answer then is if you can't get them up, you're in trouble. But it's equivalent to not being able to get the landing gear down on a transport. It's about the same order of risk and complexity.
The XV-15 has been a remarkably reliable research aircraft. During its 5-year, 600-flight-hour career, the conversion system has never failed to safely function. To control a hybrid air vehicle like the tiltrotor, a hybrid flight control system is needed.
It has to have the control system of a helicopter as well as the control system of an airplane. Well, first of all, the airplane controls are always working. The ailerons and the elevators are always moving, even in hover. They don't generate any moment because there's no air flowing over the surfaces. And then, as the aircraft transitions into forward flight, these aerodynamic control surfaces become effective, and the helicopter controls are phased out.
The XV programs were defined by the creative use of existing materials.
And it wasn't off the shelf. You know, a lot of the components are off the shelf. There's Huey pedals, and there's 205 drive shafts and engines out of a Cobra. So that pretty much dictated how the aircraft was designed.
The summer of 1977 saw the rollout, pre-flight system checks, and the maiden hover-only flight by aircraft number 702, the first of two XV-15s built. With gear locked down and pylons fixed, 702's inaugural flight explored the helicopter handling qualities of Bell's second-generation tiltrotor. The XV-15's first flights confirmed the docile handling qualities that had been predicted. The pilot workload and tasking, when compared with other VTOL concepts such as tiltwing or fan-and-wing, proved to be very good.
Yes, yeah, it does. In fact, when people come through the hangar on a tour, I quite often, depending on their level of technical knowledge, I tell them that the airplane is really easy to fly, and it is. I've said that I could put anybody who has piloting experience, whether it be helicopter or fixed wing or both, put them in there, and with a thorough briefing before that, of course, put them in the right seat, and I could sit over there and coach them through a flight and never probably have to put my hands on the controls. It's really that straightforward.
Pleased with the early results, NASA, the Army, and Bell moved to the next phase.
Ship number 1 was flight tested in hover mode only and was shipped to NASA Ames by C5 and reassembled out there and put in the wind tunnel. We took a little bit of a different approach on the XV-15 in that every part of the conversion corridor was proven in the wind tunnel by remote control first. Ship number 2 was then completed and stayed at Bell for a short time, and as the wind tunnel data was developed and the conversion process was proven, we would actually fly the same profile at Bell with the second aircraft, with the same crew, by the way. The crew that flew the remote control XV-15 in the wind tunnel would come back to Fort Worth and fly the ship number 2.
The first complete conversion from helicopter mode to airplane and back took place in 1979 in Fort Worth. Bell participants remember the event as predictable. 703's performance validated their experiences in the lab and wind tunnel. .703 then moved to Ames, while 702 was readied for its coming out tour.
Both aircraft ended up at Ames, actually at Edwards Air Force Base, for a short time, and this is in the late 1980, early 81. And ship number 1 was pulled out of the wind tunnel and refurbished back into flight condition, and it's the aircraft that went to Paris.
The Paris Air Show, 1981. The aerospace community was literally stunned by 702's effortless performances at Le Bourget that summer. On a daily basis, 702 displayed its excellent hover, conversion, and airplane modes of flight without a hitch. The Paris Air Show was a perfect venue for the international tiltrotor debut. Held every 2 years, attended by buyers and sellers from around the world, including the communist bloc, Le Bourget is the showcase of military and civilian aerospace technologies, where ideas and concepts are displayed, judged, and debated. For the XV-15 and tiltrotors in general, the Paris show drew a great deal of attention to this evolving, apparently mature technology.
I think the XV-15 was a natural follow-on. The XV-3 proved the concept was valid. The XV-15 proved that the analytical models were correct and that we could produce an aircraft that had solved the early problems. You know, the concept, all along, the concept was valid and everyone believed in it. It was just a matter of whether or not you could build it. Kind of like today's fighters, where finally, after all these years, we've got swept forward wings where we've known for 30 years that's the way to go, that's the most efficient way to go, but we couldn't build them. So the XV-15 proved that you could build the concept.
The tiltrotor configuration offers many advantages. Unlike the Cessna Citation jet shown here, a tiltrotor doesn't need a long, costly, and often crowded runway. But as you can see, the tiltrotor can accelerate and cruise at fixed wing speeds, traveling from point to point with good fuel efficiency, low cabin and exterior noise levels, and low levels of vibration. Fuel efficiency and noise qualities are due in part to the design's relatively slow rotor blade rotation. In helicopter mode, an XV-15's prop rotors turn at only 589 revolutions per minute. When cruising as an airplane, rotation speed slows to 517 RPM. When in the partially converted configuration known as tiltrotor mode, the craft displays excellent VTOL flight characteristics as seen in this minimum ground roll liftoff. This short takeoff demonstrates how the XV-15 could increase its payload by 25% over that possible during a vertical liftoff. Maneuvering like this down the length of a runway is one way of demonstrating the ability of a student helicopter pilot to coordinate several flight tasks at the same time. Here, the XV-15 displays its good helicopter handling talents much like a student pilot. A vehicle that can take off, climb, and turn within a confined space like 702 is doing here has potential as a major player in civil and military aviation. This capability alone in city center operations would keep all low-altitude tiltrotor activities over the vertiport or airport boundaries. This ability to operate in confined or rugged terrain without runways, when combined with tiltrotor speed and range, has great appeal to military tacticians. Unlike helicopters and airplanes, tiltrotor can point its nose independently of airspeed or, to a limited extent, direction of flight. Airplanes and helicopters can do that briefly, but not long enough to land on steeply sloping ground or improve forward visibility while operating around an air terminal or over a battlefield. In order to determine if the tiltrotor concept was applicable to the Joint Armed Force requirement for a new generation of medium-lift, vertical flight-capable aircraft, a series of U.S. Navy-funded tests took place in the early 1980s using 702. Sikorsky's CH-53 Super Stallion is a heavy-lift helicopter that is refueled in flight by the Lockheed C-130 Hercules. JVX suitability test results demonstrated that a tiltrotor could perform the tanker mission for the 53 without forcing the big helo to fly at maximum speed, as it must with the C-130. Tiltrotor's cruise speeds mean it can refuel from the C-130 without forcing the Hercules to fly at minimum speed, as it must with the Super Stallion. This flexibility means that the tiltrotor can serve in both capacities for a wider range of other aircraft types, from rotorcraft to jet. In air combat maneuvering tests, the ability of the tiltrotor to survive and win against potential adversaries was evaluated against aircraft ranging from helicopters to fighters. Between 50 and 150 knots, tiltrotor was clearly the more versatile aircraft. If the jet didn't get a successful shot off on its first pass, there was a good chance that the tiltrotor would be able to maneuver and bring its weapons to bear before the jet could turn and fire again. The suitability tests also addressed the need for shipboard operations. There was concern that having one rotor over the edge of the deck might create control problems for the pilot. This didn't prove to be the case. On LPH-10, the USS Tripoli off the California coast, XV-15 number 702 demonstrated its ability to operate over the deck edge and perform short takeoffs under various wind conditions. These shipboard tests also provided data about tiltrotor spotting or parking requirements on space-conscious ships. The effect of tiltrotor's configuration on external lift operations was also evaluated. Its diffused downwash and ambient noise levels proved to be an improvement over medium-lift helicopters currently used for such missions. The tiltrotor proved ideal for search and rescue. Good all-around visibility, speed and hover performance, endurance on station, reduced downwash and noise all combined to make tiltrotor a great candidate for this mission. The ability to operate from all types of terrain is a necessity for any aircraft used to evacuate wounded, carry troops and weapons, and function in austere environments. With its pivoting rotor pylons, landing on slopes that would stymie airplanes and helicopters alike is an easy task for tiltrotor. Tiltrotor's ability to control speed by pylon movement without changing the position of the nose relative to the horizon makes it a likely candidate for the challenging high and low speed nap-of-the-earth missions close to and behind an enemy's front lines. A major component of modern military helicopter strategy calls for the extensive use of terrain as a mask or cover for concealment. That terrain can be anything from desert to ice pack, tundra to rainforest. Whether cactus hopping through the desert or skimming along the surface of a narrow river channel, tiltrotors have displayed the agility, speed control, and precise handling needed for such demanding rotorcraft missions. Military tiltrotors will prove hard to track for hostile anti-aircraft fire control systems. Their speed, ability to use terrain masking techniques, low noise, and reduced infrared and radar profile mean tiltrotor can melt into its surroundings. These superior qualities explain why a tiltrotor, the V-22 Osprey, has been chosen as the vertical medium lift aircraft for the United States Marine Corps in an air assault role.
It's the key to it. We are looking for something that will give us the ability to maneuver and stay out of harm's way, if you will. The Osprey gives us that capability. Let me build a scenario for you, if you will. There's three things you want to do when you take off in a combat environment. First is, don't get shot. Second of all, if you get shot, stay in the air. And the third is, if you fail at the first two, be able to walk away from the smoking hole. All right, now, what have we done with a V-22, or a tiltrotor, if you will, that you couldn't do with a helicopter? First of all, inherent in the design of the tiltrotor, if you go back to number one of don't get shot, it's traveling at twice the speed of a helicopter. And because it's so quiet, you can hear a helicopter 4 times as far away as you can the tiltrotor. Now, what that does is it gives the enemy gunners 8 times the warning of a helicopter coming than a tiltrotor. Now, once he does come in sight, we've used the latest technology on this. Again, he's traveling twice as fast, so it's much harder to hit him. You have less time to shoot him. Then we've added all the latest technology that we've learned from the various conflicts that everybody's been in to try to keep the airplane in the air. It's a fly-by-wire airplane. Most of the hydraulics are gone. It's got 10 times the ballistic tolerance of the CH-46, the airplane it's replacing. It's got self-sealing fuel cells. We pump nitrogen into the cell, so in case it does take a hit, the cell won't blow up on it. Numerous items like that. So that kind of takes care of number 2. And then number 3 is, if you do go down, if they manage to hit you and they knock you down, on present-day helicopters, all the weight, the mass of the transmission, the motors, right on top of you, right where the people are. So as you hit the ground, it comes crashing into the fuselage and does a lot of damage. And if you're lucky enough to survive that, then the rotor system starts slicing through the fuselage. In the V-22, they're out on the wingtips, and the wings are designed to break off clear of the fuselage. So we think we've covered steps 1, 2, and 3. If you then add that to the range and the speed that it gives us, or essentially the ability to fly where the enemy's not, and you add it all up, you can see why the Marine Corps is so excited about the V-22.
The Marines will use the MV-22 Osprey to replace their CH-46 Skyknights. They will receive 552 aircraft.
Our CH-46 right now is our bread and butter rotorcraft for assault. That's the one that we go into. It's a 1960s technology. It's restricted by helicopter speeds, if you will. It has restricted range and it has restricted lift capability, and they're getting old. They have to be replaced. One way or another, they have to be replaced. Now, if you do this about every 30 years, so it's not something that happens every time. What we're building now is going to carry the next couple of generations of Marines into combat. Do you just want to build another 46 with its known restrictions, or you want to go for the new technology that'll give them that fighting chance to survive in the year 2000? Well, obviously, we opted for the new technology. Give us the speed, give us the capability to get into combat and live.
Osprey will be as useful and used as a Swiss Army knife. This cutaway reveals how tiltrotor features the best of airplane and helicopter in one vehicle. The 40,000-pound V-22 is an unprecedented multi-service aircraft program, providing a common vehicle to every branch of the U.S. Armed Forces. Using the latest in computer-aided design and manufacturing processes, the tiltrotor team of Bell Helicopter and Boeing Vertol is building a machine for many missions. The Army's MV-22 will perform combat logistics, resupply, and medical evacuation missions. The Navy will initially receive 50 HV-22s for combat search and rescue, with the possibility for 300 more for use in anti-submarine warfare. Strike Team Transportation is the Air Force mission for Osprey, and they expect their CV-22 to play an important role in anti-terrorist operations. As unusual as this multi-service program will be, its acquisition will also break new ground. Under a unique Department of Defense procurement policy, the Tiltrotor team of Bell Helicopter Textron and Boeing Vertol Company will pay for their own manufacturing tooling. Both contractors have also agreed to stringent conditions of acceptance and performance.
Yes, it's the model of Navy procurement. We try to introduce cost control for the life of the program. We have competition as our cornerstone. We have a fixed price development, which I believe is the first airplane that's really gone into a development where it's fixed price. And then we have two contractors building the airplane. When we get into production, we're going to place them one against the other so we don't get caught in that sole source environment where I told you it was going to cost $10, but now I'm the only game in town, it's really going to cost you $25.
A valuable aircraft like Osprey will not be inexpensive to build. Estimates vary, but the V-22 will certainly cost more than either a comparably sized helicopter or airplane.
I can give you numbers that range all over the ballpark. Let me give you the easiest one to understand, which is what we call recurring flyaway. And that's as the airplane flies over the factory fence, what's the cost of everything that's in it and on it. And that'll average about $16 million a copy.
Bell will be responsible for developing the wing, nacelles, prop rotor, and drive system assemblies. One advance here is nacelle access cowls with built-in work platforms for easier maintenance. The 6,000 horsepower turboshaft engines, the T406 AD400 built by General Motors Allison Division, are a low-risk component that evolved from previously successful Allison power plants. Like the XV-15, the V-22 will have single-engine capabilities. Alan Shane.
There's an interconnect shaft between the two rotors connecting actually the drive systems in each nacelle across through the wing. The cross shaft or the interconnect shaft is normally unloaded, and so it would only pick up torque in the event of something like a rolling motion of the aircraft loading up one side and unloading the other, or in the event of an engine failure.
Osprey has an ingenious way to facilitate operations on board ships.
We also have designed it so that it folds up. The propellers, if you will, index and all fold in along the leading edge of the wing. Then the entire wing rotates to align itself with the fuselage. All this, by the way, can take place in a 60-knot wind in 90 seconds. It doesn't fly very well when it's in that configuration, so we can undo it in a 60-knot wind in 90 seconds, too.
Boeing Vertol is responsible for the fuselage structure. The cabin is 24 feet long, 6 feet wide, and can seat 24 combat-equipped troops. The cockpit is designed for a pilot, co-pilot, and crew chief, and features 3 large, multi-function cathode ray tube displays at both the pilot and co-pilot stations. These displays are also compatible with night vision goggle systems. The large protrusions on either side of the fuselage are called sponsons. These will carry fuel and house the landing gear. The V-22's tail or empennage section consists of horizontal and vertical stabilizers, rudders, and an elevator. A major factor in tiltrotor selection by the armed services is its ability to self-deploy. The Marine Corps helicopter it replaces cannot. If this aircraft offers such advances in performance and capabilities, why wasn't it built sooner? One possible answer: as much as the tiltrotor concept is a blending of diverse elements, the modern Osprey is made up of many make-or-break technologies, like composite materials, fly-by-wire flight controls, new prop rotor structures, and aerodynamics, all of which have only appeared in the last decade or so. The coming of the Osprey will usher in a new era in military flight. To say that our air transportation system has capacity problems is stating the obvious. Runways, terminals, access roads, neighboring highways are all straining under the load, particularly in the northeastern United States. All-weather operations dictate costly snow removal efforts to keep these roads and runways clear.
We are experiencing considerable congestion in the metropolitan New York, New Jersey region. Our 3 airports are currently handling some 80 million passengers a year. And with the projected growth in traffic, the existing congestion will probably worsen. So we look to solutions to to increase capacity and alleviate the congestion. And we view this as a possible, the civil tilt rotor, as offering a possible new, totally VTOL short-haul transportation system that would operate city center to city center. And if that should prove feasible, that would allow the diversion of some of the short-haul traffic, say New York to Washington, New York to Boston, to be diverted from LaGuardia and Newark in particular, thereby creating additional capacity at those airports and creating a whole new system using downtown facilities.
For many travelers, getting to and from the airport, struggling through a crowded terminal and suffering departure or arrival delays takes longer than the flight.
In a typical commuter run, say if I were a businessman going from Washington, D.C. to New York City, if I were in the city center, I'd either take the metro or a taxi and get a land segment ride out to the national airport. And then I'd go in the airport and I'd wait in line to get on board one of the Eastern shuttles or the Pan Am shuttles going up to the New York area. Typically, once I'm on board the airplane, because of the air traffic congestion and the problem of gates at the other end, I might sit on that aircraft for a 35 to 40-minute delay just waiting to take off. Once we've been cleared to back off from the gate, we typically will take about 15 to 20 minutes waiting in line to get to that concrete runway. All of the airplanes taking off have to line up one after the other to leave from the runway, and therefore we wind up with a further delay there. Once en route, the jet airplane is traveling at 400 to 500 miles an hour and goes directly up there, but then it has to line up in that long queue of airplanes waiting to land on that long concrete runway again. And so he's out there mixing, slowing down and positioning himself to be able to do that. Once he lands, he taxis into the gate, and the commuter gets off. He gets a taxi into New York City, another 45-minute segment. So the entire trip, instead of just taking that 1 hour from airport to airport, really consists of 2 land segments and an air segment. When you total those up, you're looking at about 2 to 2.5 hours worth of travel time and the additional cost of the 2 land segments. The tilt rotor, by contrast, is able to pick you up at a downtown vertiport, fly you in 45 minutes to New York, and land at a downtown vertiport in the vicinity of the business you want to do.
It's fairly certain that existing airports will have to serve the medium and long-haul markets in the future, since there is, understandably, opposition to new jetport construction.
The problem of communities in creating any new facilities is a very formidable one. Okay, we've had experience in the past where we endeavored to build a new jetport. That was in the 1960s. And the people in the area of the site that we had selected violently opposed the project and succeeded in bringing political pressures to virtually prohibit any such facility. All of that is to say that you can't underestimate the importance of the communities. And we would hope, though, that by demonstrating how quiet the aircraft is and that the ability to locate these along the waterfront where you can take off over water, that hopefully the communities might accept such a facility.
To be successful, tilt rotor will have to overcome 2 obstacles which have hindered city center to city center helicopter airline operations.
Generally, it's been the high operating cost of helicopters and also the absence of an infrastructure to take advantage of its capabilities. In general, a tilt rotor will have 2 to 3 times the speed of a helicopter. So the productivity basically doubles or triples. So you reduce the seat mile cost by 1/3. Correspondingly, because it's a combination fixed wing and helicopter, enjoying the best of both worlds, its initial investment cost probably be somewhat higher than a comparable helicopter. But overall, the benefits of lower operating cost and higher speed will bring the seat mile cost down, will be competitive with fixed wing to the extent that the infrastructure must be in place to permit you to fly center city to center city.
The advent of this infrastructure is the key to exploiting tiltrotor's characteristics.
As far as future heliport development is concerned, it will evolve through the natural process, which is local community support through the FAA regions to the headquarters, where the proposal to build downtown heliport or publicly owned heliport will be included in what we call our National Plan of Integrated Airport Systems.
Another significant hurdle is Federal Aviation Administration certification of a commercial tiltrotor.
Over the years, we have developed an interim criteria for powered lift, and we intend at this point to use that as the baseline for determining the certification criteria for a civil tiltrotor. Of course, we'll take all we can get from the experiences of the V-22 as we go along.
I think it might be good to point out, though, that in coming to the decisions that we will ultimately come to on the appropriate certification standards, our end objective is to give the traveling public the level of safety that's consistent with what they now enjoy in fixed-wing transport category aircraft. The details, which will require a lot of work, a lot of public conferences, will be tailored to the tiltrotor technology. But our basic safety objective is to give the traveling public transport category level of safety.
In Europe, serious efforts are underway. Several aerospace concerns have formed a consortium called Eurofar to develop and build a civil tiltrotor. This group recognizes that tiltrotors represent an entirely new transport system requiring public acceptance, new facilities, and new rules, as well as revolutionary new aircraft. The performance of the XV-15 at Paris in 1981 was an impetus to this venture. The countries represented are almost mirror images of Airbus Industry, a consortium that has and is carving out a large slice of market share in the passenger jet business.
The French have had an interest in the tiltrotor technology for a long time. In fact, they've done a lot of research in this area. But recently, 6 European helicopter companies have gotten together and formed an entity called Eurofar. That stands for the European Future Advanced Rotorcraft. And they're a very powerful group of companies with a lot of technical expertise. And their objective is to design and build an 18 to 25 passenger tiltrotor commuter aircraft to capture that potential market out there. Presently, their timeline looks at having an aircraft fly in the early 90s, and to be able to have that, I believe, in the 95 to 96 time frame. So we're looking at a very real threat to having the European countries capture a large portion of that market. In addition, the Soviets have been identified as having an interest in the tiltrotor technology. At the 1981 Paris Air Show, where we took the XV-15 and demonstrated that technology to the world, one of the Soviet engineers there told me that for a long time he had wanted to start a tiltrotor program in the Soviet Union, and perhaps now he could. Since that time, there have been reports in the press that the Soviets have 2 tiltrotor designs, the Mi-30 and the Mi-32. So the interest there is considerable.
Why is it so important for the United States to take the lead in developing civil tilt rotors? One segment of U.S. industry that has held its own with respect to the balance of trade has been aerospace. For years, the U.S. built the free world civil jet planes, helicopters, and short-haul aircraft. Today, we see tremendous inroads being made into the U.S. market share by very high-quality aircraft built in countries like Brazil, Spain, France, Britain, Ireland, Italy, and Sweden. If the U.S. does not capitalize on its lead in tiltrotor technology and do so quickly, many experts feel that U.S. commercial operators will end up buying civil tiltrotors from foreign manufacturers.
Well, I really think that that is very possible because the countries such as Europe really see the potential, favorable potential that the vehicle has in their country. And they are addressing it from a national standpoint and really focusing on the civil applications. Whereas we, of course, are concentrating on a military version, which is of course, very important also. But the fact that they're addressing the civil version, and their economic system is different in that they have essentially a partnership of the civil industry with the government, and the government underwrites the high risk of such developments, really does offer a very strong possibility that they would be first in the marketplace.
With a 30-year development history and the successful track record of the XV-15 proof-of-concept tilt rotor, it is clear that this technology is ready for widespread application. The opportunities in both the military and civilian markets here and abroad are numerous. If the United States capitalizes on the current technological advantage it now enjoys due to the investment and efforts of the private sector and government by following the V-22 program with an aggressive and systematic approach to a civil program, the U.S. could realize significant economic benefits. Civil tilt rotor's success hinges on the development of a completely new and independent transportation network of vertiports and ground access. Support for tilt rotors is widespread, but some question its high purchase cost relative to payload. Others doubt whether developing a completely separate air transportation system is possible. The military's commitment to tilt rotors is definite and for the long term. Many feel that we're barely scratching the surface of tilt rotors' military potential. For example, gunships and small, remotely piloted tilt rotors could appear in the next wave. The Soviet Union has confirmed by imitation the tactical value of this emerging aircraft type. In the late 1940s, some felt that the helicopter was only an interim and limited answer to the need for vertical flight. They believed a convertible aircraft combining the vertical lift of helicopters with the efficient, high-speed horizontal flight of airplanes would someday emerge as an entirely new and distinct chapter in aviation history. They waited and worked for over 40 years to achieve that dream. The age of tilt rotor is now.